This study tackles a major issue in large vision language models, or LVLMs, which are advanced AI systems that combine visual and textual data for tasks like visual question answering, or VQA. The core problem is that these models often generate hallucinated content, meaning they produce incorrect or fabricated information, while appearing highly confident in their outputs. This can be dangerous in safety-critical areas like healthcare or autonomous driving, where unreliable predictions could lead to serious errors. The researchers, Yuanchang Yi and Yanwen Wei from the School of Data Sciences at Zhejiang University of Finance and Economics, propose a solution using a framework called Split Conformal Prediction, or SCP. This method is designed to quantify uncertainty in LVLMs without making assumptions about the data's underlying distribution or requiring the model to be retrained. By doing so, it helps filter out low-confidence outputs and provides statistical guarantees on the accuracy of predictions. To understand this, let's break down how SCP works. The framework starts by splitting the data into two parts: a calibration set and a test set. Using the calibration set, the system calculates what's called nonconformity scores. These scores measure how much a model's prediction deviates from the expected outcome, based on the data's exchangeability, meaning the data points are treated as if they could be in any order without affecting the results. Once these scores are computed, SCP constructs prediction sets for new inputs. A prediction set is essentially a group of possible answers that the model outputs, rather than a single confident choice. The key here is that this process includes a user-defined risk level, denoted as alpha. For example, if alpha is set to 0.05, the prediction set is designed to cover the true answer at least 95% of the time, ensuring that the empirical error rate stays strictly below alpha. One of the main innovations in this approach is the rigorous control of marginal coverage. This means the method guarantees that, across all possible test samples, the true outcome will be included in the prediction set with a probability of at least 1 minus alpha. It's a way to enforce reliability without relying on heuristics or approximations that other methods use. Another innovation is the dynamic adjustment of prediction set sizes. As alpha changes, the size of the prediction set adjusts inversely. For instance, if you want a lower risk level, like a smaller alpha, the prediction set will include more options to ensure coverage, effectively filtering out anything that's not confidently supported by the data. This helps in eliminating low-confidence outputs, reducing the chances of hallucinations slipping through. Importantly, this framework doesn't require any prior assumptions about the data distribution, and it doesn't need the LVLM to be retrained. That's a big advantage over traditional calibration techniques, which often demand expensive retraining and can falter when the data distribution shifts, like in real-world scenarios where inputs vary widely. The researchers extend SCP specifically to multi-choice scenarios in closed-ended VQA tasks. In these tasks, the model selects from a predefined set of candidate answers. By integrating cross-modal consistency verification, the method checks how well the visual and textual elements align in the model's outputs, further enhancing its ability to detect inconsistencies that might indicate hallucinations. To test this, the study evaluates the framework on popular benchmarks like ScienceQA and MMMU, using 8 different LVLMs. The results show that SCP delivers on its theoretical guarantees across all alpha values, meaning it maintains the desired coverage rates consistently. Moreover, the framework performs stably even when the split ratio between calibration and test sets is varied, demonstrating its robustness for practical use. This robustness is crucial for real-world applications. For example, in healthcare, where LVLMs might analyze medical images and answer questions about them, this method could flag uncertain predictions, preventing misdiagnosis. In autonomous systems, it could help ensure that decisions based on visual data, like recognizing road signs, are reliable and not based on fabricated interpretations. Overall, by bridging the gap between theoretical reliability and practical deployment, this work offers a scalable way to handle uncertainty in multimodal AI. It focuses on dynamic threshold calibration and cross-modal checks to provide real-time, trustworthy outputs, making it a valuable tool for advancing safe and effective vision language systems. The study highlights how processing visual and textual information together increases hallucination risks, But with automated detection like SCP, these risks can be mitigated without prior knowledge or complex setups. In the broader context of AI research, this approach builds on prior work in uncertainty quantification for natural language generation. While methods like verbalized uncertainty or probability calibration have been tried, they often fall short due to overconfidence or the need for retraining. Conformal prediction, as used here, stands out because it's model-agnostic and computationally efficient, allowing it to be applied directly to pre-trained LVLMs. The evaluations underscore that SCP not only enforces statistical guarantees but also adapts well to different scenarios, paving the way for more dependable multimodal AI in safety-sensitive domains. This includes areas like education, where models answer science questions, or everyday applications where visual data informs decisions. By eliminating the need for heuristic approximations and focusing on data-driven calibration, this framework represents a step forward in making LVLMs more accountable and user-trustworthy. It's a reminder that as multimodal models grow in complexity, integrating robust uncertainty measures is essential for their ethical and effective use.